this is some classical example that what we can see. It's the high, windy environment, like the flow is coming this way, and sometimes we can see a lot of trees just knocked down. Um, so this is, we said, this is the drag, right? So we mentioned at the very beginning of this lecture that it is just combination of two forces. So one of the most classical example is the aircraft, the airfoil. So this is the airfoil. So this solid one, it is airfoil, okay? And I told you, it is combination of two force. One is pressure and another one is shear force. Shear force, it always acts to the flow directions. If the flow is going this way, so this is flow, shear force will act this way. If the flow is going this way, pressure always acts in the normal directions. So here you will see this arrows, you can see all these arrows, this is actually the shear force. And these arrows, I can use different color. This is actually the how pressure force is acting. Okay, this is the pressure force. You understand what I mean? You just connect it from here. Pressure acts in the normal direction. That means it will make 90-degree angle from every. So you see, if you see here, it will make 90 degree. And due to the viscous effect, the shear force, it always acts near the wall in the flow directions. So now what we did, we highlighted this small section. If you want to calculate the drag for this whole domain, you need to just make a summation of all of these force throughout the streamline, throughout the body. So here we highlighted these very small sections. So you see, this is the shear force and this is the pressure, how it's acting that way. So we can say the shear is T omega and pressure is P. We use, this is very small area, so we multiply dA. So that means now it is shear force, this is pressure force, and it is changing every directions. It makes if it you can see, now we did some analysis with the change of the angles. So then we'll get the cos theta sin theta, that means in different directions. So you do not need to know what it is. When we do all these calculations, we will get the drag force is this, and this is the lift force from this. So you need to do a lot of calculations. You do not need it even in real life. So you can say what you are talking about. I know some of you will do your project in coming days. And then if you want to calculate the drag and lift, basically, if you do some computer simulation and use if you develop your own code, then what you need to do to calculate the drag and lift, you need to use this formula. But when you're talking about in real case, we can calculate it by using some tools, and we do not need to use it. We do not need to use this formula. And importantly, most importantly, we are not interested for this whole shear and the pressure variations, but we are interested in the total drag and lift. So this formula is useless for us, but this is important for you if you are planning to do a project, you are planning to use some computer software, you are planning to develop your own model, numerical model, then you need to use this equation. So that's it, and you do not need to worry about this slide. Now, I will discuss this one. You see, it is some sort of analytical presentation, and this is some real figure from some CFD simulation. Just try to concentrate for next 1 or 2 minutes, because what we're going to discuss here, it will be important for the rest of the lectures. We have, this is a vertical plate, flat plate. This is a flat plate, and if you look, the fluid is flowing in these directions. Who can tell me, is it parallel directions or the perpendicular? Like the flow is flowing this way, we have the vertical plate. Is it parallel, like the force, is it just, or the flow, the fluid flow, is it acting on that plate kind of parallel or perpendicular? Is the entry, is it perpendicular? Or in other words, yeah, it's perpendicular definitely, because it is a vertical plate. So here it is parallel. In this case, if you clearly look here, we said this is figure A and this is figure B. And if you see here, for A, the drag force on this parallel plate, and this is perpendicular plate or normal plate, but this parallel flat plate, it will depends on the wall shear only. No pressure force. Actually, here, the fluid is flowing this way, and this is our shear force. So the only we have the shear force which is acting. So this is the flow directions, and the shear force is also in the same directions. So in this case, yeah, no slip condition is something that viscous effects. Yeah, we'll discuss it actually when we'll discuss the boundary area. Yeah, that's true. So no slip is, this is due to the viscous effect. Yeah, so I'll explain it later on. So in this case, we're getting only the shear force here, no pressure force acting on this direction. So due to the shear, we'll have only the wall shear, and the drag, it will be due to the shear force. So you can say it is friction drag. In other words, the shear force, or you can say this is the friction drag. We have no pressure drag in this case. When it is kind of the parallel, it is just the flow is just flowing parallel to the flat plate. But when it is perpendicular, now this is, the scenario is different. When it is the perpendicular, then, or normal directions, then you see it is the only the pressure force. Now you look here, this small arrows, this is the shear force, this is the shear force. So it is not in the flow directions, so it is in the opposite directions, but the pressure force is acting in these normal directions. So we will have the pressure in these sections, and what will happen, we'll have definitely high pressure here. This is a solid body, it is blocking all the waters, all the airs. So that means in this case, it will be kind of a wake reason or circulatory reason. The flow is going this way. Maybe they will meet in this section, but we will get a reason where there will be kind of stagnation scenario. And in this case, we will have literally low pressure, nearly zero pressure in this section. When there will be pressure variations, it is high pressure, this is low pressure. So it means we will have the high pressure drag here. And it is all about pressure drag, no, the wall shear drag or the friction drag, because the friction, it is in the opposite direction, it's not in the flow direction. So what we understand from here, to get this drag force, it has to be in the same direction, in the flow directions. And that is why when we're talking about the parallel flat plate, then we have only the wall shear or the friction drag. But when it is the perpendicular one, then we'll have the pressure drag. And now this is two case. And you see, you can validate this. What I claimed, I said here will be high pressure, low pressure here. So this is our this is the flat plate. This black one, it is the flat plate. You see we have the high pressure in this section, and you see we have the minimum pressure here, and this is the flow contours, like how the separation is happening. Similarly, it is the here it is the vertical in the parallel flat plate. So here you will see when it is near the wall, the flows we'll discuss the boundary layer. I'm not going to discuss boundary layer now, but maybe in 30 to 40 minutes I'll discuss the boundary layer. So if I want to discuss everything altogether, then it will confuse you. So think about it. It will only depends on the flow directions. And now, so two case, for this case we have no pressure drag, for this case we have no shape, the friction drag. Now what will happen when we have an airfoil? It is kind of a asymmetric shape, and it has some sort of angle of attacks. It's kind of the aircraft, and we have some angle of attacks. Then what is happening? You all know I discussed this previously. This is the streamline going this way. We will have the low velocity here. That means the high pressure in this section, low pressure in this section. So we'll have the both in this case. So it will act normal to the normal direction. It will act also the parallel direction. So we'll get here the lift force. We'll get the pressure, or we'll get also the shear, the wall shear. So I will discuss it later. You see here how it looks like. This is some theoretical claim that at the bottom we'll have high pressure, at the top low pressure. You see this computer simulation is showing it is green. It means it is nearly that's called this is the contours, the legend. So it's showing it's the high pressure in this case, it is the low pressure in this case. So the high pressure means it will experience some sort of pressure in that way, and that's the lift force. The difference between these two, this is the lift force. Anyways, I wanted to discuss these two things because we have got a couple of slides later on, and then it will be more clear. Now I'm moving to the next phase. Okay, is there some question in the chats? No, okay. So now previously I showed you that mathematical expression for the drag and the lift for the entire body. But I mentioned this is not what we were looking for, but we are looking for the total of the resultant or the final drag and the lift value. And here is the formula. For the drag coefficient, it is the formula. For the lift coefficient, this is the formula. Here, this FD, it is the drag force. FL, this is the lift force. If you know your drag force, you can easily calculate the drag coefficient. If you know the lift force, you can easily calculate the lift coefficient. And we have a lot of other sources, charts that we can use for different geometry. So one important thing you need to keep in mind, you're going to complete, you need to prepare the wind tunnel report. It was due this week, end of this week, so I have extended it. So now it's due on week 12. Another important thing, if you just need to keep in mind no special consideration application will be approved um, because we already extended this submission um, 1 week. So no further extension will be approved for this assignment because we need to actually submit the marks. We have some internal deadline, and yeah, so that everyone needs to actually keep in mind. And some of you sometimes ask for an extension at the very last moment, and any special consideration application, it should come through proper channel, not through the emails or the team messages, but it should come through the university. And but for this one, we already approved 1 week, so there will be no more extension. But what I was trying to say, this is very important. The frontal area. The frontal area is important, and another term you will see, it is the planform area. Okay, so when we calculate the drag and lift for a cylinder or a sphere or a moving car or any running objects, we actually use the planform frontal area. Can anyone tell me what is the frontal area? Can anyone tell me what is the frontal area? Any idea? So yeah, so that's like, you can see my face. So this is, if you look at this way, yeah, from the front view, that's the frontal area. Then what you can see if you look from the front view, so that's the frontal area. The planform area is, we have an airfoil. If you look at this from the top, okay, so from the above of the objects, if you look at that directions, that's the planform area. When we analyze the airfoil, actually we will use the planform area. For other cases, we'll use the frontal area. So I'll explain it later on. Here,